hopefully soon, the James Webb Space Telescope is going to launch. And even more hopefully that if you're watching this video sometime in the future, then I can say the James Webb Space Telescope did launch and it didn't blow up and it didn't fail to deploy and it's doing its thing and it's doing science. And it has been rightly touted as the successor to the Hubble. It is a massive telescope. I've done videos on James Webb. I'm excited for it. I've only been waiting a decade for it to launch, but now it's finally out there doing science. So what's next? And so this episode is going to be the top 5 space telescopes to look out for after James Webb. What are we going to get hyped up for now? Well, starting with number 5, and by the way, this is presented in no order whatsoever, except these are 5 things. So don't think I'm liking one or the other. It's just five telescopes. That's it. Number 5 is the Nancy Grace Roman Space Telescope, scheduled to launch in 2027, but don't hold your breath on that. You know how the whole James Webb thing went out. Anyway, it's been delayed a lot because James Webb has been delayed a lot, and so that's the Roman telescope is the next thing to come after the James Webb. So yeah, it got pushed back a little. In fact, it probably should have been in space already. This telescope has been had a very interesting history. It started out actually in the late 90s and early 2000s, these concepts called JEDI or JDEM, the Joint Dark Energy Mission. I forget what JEDI stood for, Joint Energy.
I don't think so.
It doesn't matter. And, but those projects weren't prioritized, and NASA selected other missions, other things to look out for. And then the National Reconnaissance Office one day said, called up and said, hey, NASA, by the way, we have a couple spare Hubbles. Do you want one? They said, really? Yeah. We just, they're sitting in a warehouse. We got nothing to do with them. They were going to be spy satellites. They should hold the phone closer. Sorry. They're going to be spy satellites, but we don't need them. And they're like, really? Like things like NASA, like Hubble costs billions of dollars. Yeah, we know, but they're extra. Do you want them or not? So NASA took them, and they're the telescopes. These are Hubble-class telescopes, 2 of them. And one of them just happened to fit the specifications needed for this kind of new telescope that these scientists hunting for dark energy wanted. And so it became a mission. It became a thing. It revived all these concepts. And the mission was originally called WFIRST, W-F-I-R-S-T, for Wide Field Infrared Spectrographic Telescope. Horrible with acronyms.
I sense a great deal of confusion in you.
It doesn't matter. But that name is also a joke. It's a little pun because the aim of this telescope was to study dark energy, this crazy phenomenon, mysterious phenomenon, where we are seeing the expansion of the universe accelerating. So what does it have to do with WFIRST? Well, in our models of cosmology and the expansion of the universe and the accelerated expansion of the universe, we don't know what dark energy is at all, but we parameterize it. We include it in our mathematics and our calculations. And one of the letters we use as our variables in the math to describe dark energy is the letter W. So WFIRST, it's a mission that's primarily going to target dark energy. Yeah, a nerd joke. Anyway, it's since been renamed to name after the former chief scientist of NASA, Nancy Grace Roman. Amazing person. A good name for the telescope, and that's his point. It is going to be a massive galaxy survey, so it's going to map out millions of galaxies, map out cosmic structures, and try to tease out the nature of the accelerated expansion of the universe from that data set. In parallel with WFIRST, the European Space Agency is also launching a similar mission called Euclid, which is pretty much going to do the exact same thing. There's going to be a lot of overlap, and that's one of the reasons WFIRST/Roman wasn't initially funded, was because, well, the Europeans are already doing it. But hey, we get 2 galaxy surveys for the price of, well, like 3 or 4 galaxy surveys probably. Number 4, we have Louvois, which sounds like a very cool French word, but it's not. It is the, I have to check my notes for this one, sorry, the Large Ultraviolet Optical Infrared Surveyor. Oh, the S doesn't get to play a role in the acronym because then it'd be LUVOIRs and that'd just be weird, I guess. But anyway, you know how James Webb is super cool, right? And it's like a mega Hubble. In fact, James Webb is so big, it's such a big mirror that it can't actually fit on a rocket. It's too big. It's wider than a rocket fairing. So they had to come up with this very clever, very cool folding origami design to break the mirror up into these hexagonal segments that folded in on themselves and packed all nice and neat inside the rocket cone. And then when it deploys, or deployed, James Webb will unfold all of its mirrors and have this giant, gorgeous mirror. The biggest mirror, the biggest telescope we have ever had in space. So that itself is a major advancement over the Hubble. LUVOIR is like that, but on steroids. We're talking about an unfolding mirror made of 36 segments, adding up to a total telescope width of over 15 meters, 45 feet. That is a giant, giant telescope. And the thought of it being up in space is just ridiculous, where it doesn't have to deal with atmospheric distortion or anything. And this LUVOIR, it's just a proposed design, by the way. It's scheduled to launch in 2039, but that's just a made-up number. LUVOIR is like the astronomer's ultimate dream telescope, where it just does everything for everybody. Like the name suggests, it's doing ultraviolet, it's doing optical, it's doing infrared, it's doing all these wavelengths of light, and it's got all sorts of science targets. Just like James Webb has a broad variety of science targets, LUVOIR will have a broad variety of science targets. Like it's going to image the early universe, the first stars and galaxies to appear in our cosmos. It's going to study Jupiter and the moons and the planets of our solar system to incredibly high resolution. It's going to hunt for biosignatures on exoplanets, looking for signs of life around other worlds. It's big. It's big. It's literally a giant telescope that's going to be what James Webb was to the Hubble. LUVOIR. Competing with LUVOIR in these proposal, early funding, where do we prioritize our next batch of money, is another experiment called HABEX, the Habitable Exoplanet Explorer Telescope, something, HABEX. HABEX is specifically tuned to hunt for life around other stars. And as a telescope itself, it's not all that super impressive. It's slightly smaller than the Hubble. But what makes it powerful, and what will make it powerful, is a star shade. See, HABEX is going to require 2 launches, one for the rocket itself and one for a very, very special object called a star shade that's going to fly out in formation with the telescope and block out the light from individual stars that the telescope is targeting. So you don't get any of the light from the star itself, and you only see the light from reflected planets. So if you're looking at a solar system or a star system, you get to block out the light, and then you can see anything around it that's illuminated by that starlight, and then you can analyze that light because it's bouncing off of the atmosphere, and you can figure out what the atmosphere is made of. So HABEX is specifically 100% targeted, focused, designed to hunt for signs of life. It's going to target Earth-like planets around other stars. It's going to use that reflected sunlight to study them, to figure out what's in there, to look for biosignatures, to look for a lot of oxygen, a lot of methane, maybe weirdly low amounts of carbon dioxide, lots of water vapor in the atmosphere, trying to determine if any of these worlds that we're seeing might be inhabited by life. Now, I do need to say, like the very day that I went to record this episode, I already made the notes, I didn't want to change anything, that the latest recommendations from the community of astronomers, every 10 years, all astronomers get together and create what's called a decadal survey, where they decide what the priorities will be for the next 10 years. LUVOIR and HABEX were competing for attention and money and priority status in the astronomical community. And the astronomical community said both, but neither. Instead of LUVOIR or HABEX, they proposed a joint mission that's kind of like LUVOIR and kind of like HABEX, that's going to be big, but not as big as LUVOIR wanted to be. but not as tightly focused on searching for biosignatures. But that's all astronomical bureaucracy wrangling that doesn't really matter. These concepts are still out there. But before I move on, I got something I want to show you. You see, this episode is brought to you by my good friends at spaceandbeyondbox.com. And you need to sign up because then you get stuff in the mail. And who doesn't love stuff in the mail, especially when it's surprise stuff in the mail? You know, I'm talking about all these NASA missions, and I have the NASA box right here. You go to spaceandbeyondbox.com/subscribe. There's a link down below, and use the coupon code Spaceman. You'll get 10% off your first order. You'll get free shipping. You'll get a surprise. It's so cool. I mean, who doesn't love cool, nerdy stuff to give as gifts for your family or friends or yourself? Because you deserve it. These are brought to you by the awesome people over at Astronomy magazine. Very good friends of mine. Very cool. And they're supporting this show, which is so cool. So every box you get stuff. You just get really cool stuff. They do put a lot of care and attention into this. So we get a magazine. We get this gorgeous postcards, Earthrise postcards. I'm opening this up for the first time. This is so much fun. Oh. It's a die-cast miniature pencil sharpener of a lander. Kids will love that. Socks. NASA socks. I am owning these. I'm owning these and I'm rocking these. That's a nice classic NASA. Like, see, this is just cool stuff. I don't know. I'm not good at guessing. Oh, sweet. A nice NASA mug. Like, how cool is this? There's more stuff. The moon box, Astronomy magazine. Oh, wow. Just cool stuff, guys. Spaceandbeyondbox.com/subscribe. Use the coupon code Spaceman. There's a link down below. Go buy something because they're sponsoring this show. They're keeping this show going, which is just fantastic. I can't thank them enough. Anyway, back to our list. So far, all the telescopes we've been talking about have been normal astronomy telescopes. Big tube, big mirror. We're going to collect a lot of light. We're going to take a bunch of pictures and spectra, and we're going to get some science. Okay, let's go a little bit weirder. Let's go with LISA, the Laser Interferometer Space Antenna. I swear I have to look up all these acronyms every single time because I'm not good at remembering the acronyms. So what LISA is going to do, it's a gravitational wave detector. That's right, it's not a normal, typical astronomical observatory. It's a gravitational wave detector. It's going to be 3 satellites flying in formation, co-orbiting with the Earth, so at the same distance of the Earth, but lagging behind in our orbit. And they're going to fly in formation, and they're going to constantly bounce lasers back and forth to each other so they know precisely how far away these satellites are from each other. So that when gravitational waves come rippling through the solar system, it will slightly change the distances between the satellites in a way that we can measure. Now, there's already been a Pathfinder mission launched to test the necessary technology, and it got the green light. This mission is being led by the European Space Agency, and it's a gravitational wave observatory in space. Now, why do we want gravitational wave observatories in space? Well, our gravitational wave observatories on the ground are really, really good at picking up a very, very high frequency gravitational wave. So when black holes or neutron stars collide, it makes a big, sharp spike in the gravitational wave spectrum that we can see really easily. But we have a lot harder time seeing very low frequency gravitational waves. These like slowly changing, slowly varying waves. It's a lot harder for ground-based observatories to pick those out of the noise. But space-based observatories are designed for exactly that. They actually won't hear the short frequency stuff because the satellites are millions of miles away from each other, but they'll pick up the very low frequency stuff. So what am I talking about? I'm talking about supermassive black holes merging. They'll see extreme mass ratio. So if a giant black hole swallows a tiny object, they'll be able to see that. They'll be able to pick up the gravitational wave signal of objects as they spiral in closer before the actual merger event. And they'll be able to detect mergers potentially even in our own galaxy. This is all stuff that's outside the hearing range of ground-based detectors. LISA is should launch in 2034. It will take another year or so to shake out everything, and hopefully they start getting detections right away. I can't wait. I'm excited for Lisa. But for our last one, for number one, let's go crazy, and I mean really crazy. There's this epoch in the evolution of the universe that we have a really hard time studying because it's dark. It's literally called the Dark Ages. It's the time before the first stars appeared. So this is after the early plasma epoch. This is after the cosmic microwave background. And then there were hundreds of millions of years where you just have all this neutral hydrogen gas floating around slowly and steadily clumping together. And then the first stars and galaxies come online, and we can start seeing them with all our telescopes like our Louvres and James Webb's and WFIRST and Romans and all that. But how you see before the first stars? Well, it turns out that neutral hydrogen emits a very particular kind of radiation. It emits radiation at precisely 21 centimeters. But this was a long time ago. And so that light, you have all this neutral hydrogen gas is emitting radiation at 21 centimeters wavelength. And as it's going through the cosmos, our universe is expanding, and it stretches out that wavelength from 21 centimeters to the present day of around 2 meters. And 2 meters, that's radio waves. So actually, some of the radio static that you might get in your car antenna is left over from this very early epoch in the history of the universe, the Dark Ages. But that radio, the fact that you have to tune into your radio to hear it is exactly the problem. The Earth is swamped by radio interference. Radio astronomy is one of the hardest fields because we're constantly drowning in radio emissions that we make here on the Earth. So let's have a radio telescope not on the Earth. This is the DARE mission, the Dark Ages Radio Explorer. It is in a satellite, in a very, very simple satellite. It's basically a car antenna orbiting the moon. And it's orbiting the moon so that it takes its observations at the far side of the moon, which is the only known place in the inner solar system that is free from human radio interference. And hopefully it can pick up some of these signals from the Dark Ages, which, by the way, we have never been able to observe or detect these emissions from the Dark Ages before. And maybe we'll be daring enough to do it. Did you like that pun? I'm pretty proud of that pun. Thank you so much for watching to the end, the top 5 list of best telescopes to look forward to in the coming years. I can't wait. I wish I could live like 100, 200 years just so we could see all the cool stuff we're going to learn about the universe. Thank you so much for watching. Thank you so much to spaceandbeyondbox.com for supporting the show. And you can support it too by going to patreon.com/PM. Sorry, there's a link down there too, and a button floating around or something that you can do. Thank you so much, and I'll see you next time.